Hello CA engineers, welcome to Passion to Flirt with CAE for CA engineers and freshers. Today in this session we are going to discuss about a static analysis setup using Hypermesh for Nastran. So what is static analysis? A analysis which doesn't possess inertia effect, then we can call it as static analysis. This is the equation what you did in your academic, F equal to K of U. So F is external force what we applied on the structure, and K is the stiffness. So how we are getting stiffness? Because of geometrical shape as well as material property, that is K equal to AE by L. U means response, that is displacement. So what are the output material property we are giving in this setup? These are the material properties, that is Young's modulus, Poisson ratio and density, and load what we are applying is 200 Newton. So this is theory calculation formula. Once we carried out analysis, you can go ahead with this one if you want to clarify whether the result is right or wrong, how we are going to evaluate, because as it is a simple problem to understand the concept, how we need to set up and how we need to validate the results, right? So this is the model. So what you can see, this is a simple plate, 100 by 100 plate is there. So one end is fixed and in another end we are applying a load, right? The thickness of this plate is 5 mm. So we can go ahead with Hypermesh. So you can use the profile as a Nastran. So can press F8 and using coordinate system you can create 0 position one node, fit in window. We can see the window, and you can go to 2D panel, and in that go to right. So in that what you can do, you can go to plane. So here mesh delete surface, so go with square, right? So this is the coordinate system, that is, so in x axis I'll put z axis. So this is the 0 position. I want 100 by 100 square, right? So create it. So fit in window. So now you can see your mesh is generated. Then what you can do? So first and foremost thing, create material property. Steel as a material property. So what type it is? Isotropic type. CAD image is mat 1. So mat 4 we are using for thermal analysis. We are not going to deal with that one right now. So go to create edit. So E means Young's modulus, that is 2.1 E per 5, right? And G means modulus of rigidity. We are not going to use this one in this analysis. Poisson ratio, that is NU 0.3, and then rho, that is density 7.89 E per minus 9, right? So then quickly we'll go ahead to create property. Okay, so what kind of type it is? So these are the shell elements, right? These are the shell elements. So type is 2D, and CAD image for this is special, and we can select this material property, create edit, right? So what is the thickness? So the thickness you can check with the presentation, that is 5 mm thickness is there, right? So come back. So assign this property to the component. So you can rename this component. So auto is, instead of that you can rename as plate, right? So if you want to change the color, you can change any color. So it is good, right? As per your wish you can change the color. So what we need to do, we created component, we did meshing, we created material property and section property. What next? We need to check whether material property assigned properly or not. So go to CAD edit. So in that you need to check with mat means material. Select this, edit it. So this is Young's modulus, percentage ratio and density, right? So then check with property, then the thickness is 5 mm, right? So come back and you can cross verify once again if you want. Press or hit F10 and select this component or element. You can see the thickness as 5, right? So once it is finished, what you can do, so you need to go ahead with the constraint. So you need to apply constraint, means you need to apply boundary condition, create. So here you can see a load collector is created here in model browser. You can see this. So then here no card image used, and even though we don't have, so analysis, go to analysis page. In that constraint is there, you can select these nodes, right? So you can apply boundary condition. So all degrees of freedom, DF1 to 6 is there. DF1, DF2, DF3 means translation degrees of freedoms are fixed, and DF4, 5, 6 means rotation direction fixed. So because 0 means what does it mean? It is fixed, right? So now you can see this 1, 2, 3, 4, 5, 6 means all degrees of freedoms are fixed. So then go ahead with force or a load, whatever you are applying. So before going to create or apply force, so first before that we need to quickly can create a load collector. Then it is created load here. So then come back. So before that, what do you need to do? You need to check how many number of nodes are there here, right? So hit shift F2 and check how many nodes are there. At the lower end corner you can see 11 nodes are there. So what is the load you want to apply? So total so 200 Newton load, right? So how many nodes are there? 11 nodes are there. So go to calculator. So 200 divided by 11 nodes. So 18.818. So for on each node 18.18 Newton load we need to apply. Go to analysis page, force. So in which direction I have to apply? This is the X direction. So I'll select X. So 18.18. So select all these nodes and apply force, right? So once it is applied, so 18.2 it is showing that 18.18 means it is round off, it is doing, right? So once it is finished, quickly you can create load step. So what kind of analysis you are carrying out? Static analysis. So then before this, so select this linear static. This is SPC. SPC means single point constraint, means each single points are constrained with all degrees of freedoms. That is SPC. So select constraint. So this is SPC, and so you can see over here constraint. This is 1. So you called 1, and load. So you can select load collector, and it is 2. The load ID or constraint IDs are respective constraint IDs or load IDs. You can see over here. So once it is done, create and edit. Then you are requesting for output. So select output. So what output you want? Displacement, sorting and format. So this sorting and format means sort 1 and sort 2 are there. We can discuss in once analysis is completed what is sort 1 and what is sort 2, and print, punch, plot. So generally you can in format you can keep print only, it is more than enough, right? And go to SPC force, sorting and format, right? And then select stress, sorting and format. So everything is done. So then once it is done, the load step is generated over here. So then we can go to control cards, select solution 111 for static analysis. These are the different analysis what you can see, but for this solution sequences for static analysis solution 1 and 1. Then come back. So param post is that this is parameter card. So output file we need to write. This is the parameters we need to control during the analysis and right. So param post, select USD post. So in this param post -1, so we are adding -1. So what does it mean? So whatever the post processing file output file is, that is, so in the format of .op2 file you can generate using param post -1. If you are adding 0 in case of -1, so you will get .xdb file. Okay, that's it. So simply we can export this file. Static analysis. So .bdf file formatters, export it, then minimize this. You can check with deck. You can open with notepad. So now you can see this is the executive control section. Okay, means what kind of analysis you are carrying out. In that section you are defining, that is executive control section. This is the delimiter means, so executive control section is finished, you can go ahead with the next section. This is next section is case control section. In case control section we constrained, we applied load. So what are the output required, what are the input required, those things we are defining in case control section. Then it was finished, we can go ahead with the next section, that is begin bulk, that is bulk data section is there. So then this is the param post is there, means so during the analysis and output request we are doing using this param cards. So these are the grades, means nodes, elements. So in bulk data section you can see all those things. So this is the deck or architecture of Nastran. So you can see this is the constraint. So one constraint is there, node ID is 1, 1 2 3 4 5 6 means all degrees of freedoms are fixed. Okay, so 0 0 0 is there, and you can see force we applied, so respective nodes. And what is the load we applied? 23.8. in which direction? The x, y, z is there, in x direction we applied. So this is the delimiter. What is that? That is anti-data. So everything, these are the node data, element data, force, everything you can see in bulk data section, right? So architecture you need to understand clearly, that is executive control section, case control section, and this is bulk data section total, right? So we can close and we can run this file. So open Nastran, open the file, run it, wait for a moment. So once run is finished, you can open this file using notepad or textpad, whatever you want you can open. So once it is open, a 4.6 file, so you need to search for fatal. If errors are there, it will show fatal error. If no fatal error, then so run is completed perfectly with no issues. But at the same time, for static analysis, what you need to do is, so you can check with epsilon value. You can search with epsilon. So epsilon value, this is the value. So what are the value we are seeing? This epsilon value. So if it is -15 is the e power -16, -3.26 e power -15 is there, then If it is less than minus e power 8, then it is not preferable. What does it mean? It is having a the whatever the model we set up, which is having a ill conditioned FE model. So we need to take care about FE modeling. This so specifically whenever you are going to carry out static analysis, this epsilon value you need to check, be cautious with this, so which will give a clear vision that whether the model, whatever the model we created, whether it is right or wrong, what kind of modeling is there, so which will give a clear hint. So in another video we can discuss more about epsilon, how we are checking, what we are checking, right? So it should be 10 to the power minus 9 preferred value. So what is the value we are getting? We are getting minus 15, right? So then, so we'll go ahead with other files. So we are getting different files. FO4, this is the total roadmap, means initial to final, what are the analysis you carried out, at what time you started, so those things it will explain. And so this file is there, no, op2 file. So I am not bothering about log file, master file, IFP data, debug data. So we'll discuss in later session, so which are very important. So we can discuss about those things. One is f of 6 and another one is op2. So this f of 6 and f of 4, why we are getting such kind of f means that this software is developed using Fortran, so that's why we are getting such kind of files, right? So we can open post processing Hyperview. So open and apply it. So once applied, you can go to contour. So you are looking for what? Displacement. Apply. So now you can see the displacement. What is the displacement we are getting? So we are getting this is the displacement. So you can see, if you want, you can set with fixed value. So you can go ahead with 6 values. This is the value what you are getting. This is the displacement value. It is the least one. So if you want to animate this one, so I am animating, but it is not showing. So to see, we can do scaling. So so now you can see the animation. So this is the displacement value. So and next what we can do, we can go ahead with, we need to check with stress value. So this is the stress value what we are getting. So we need to cross verify whether stress and as well as displacement we are getting right or wrong. So for that we need to use, this is the basic formula. So force upon cross sectional area. You all guys know this formula. So cross section means specifically, see, you can see cross section, you need to see this cross section. Area means this cross section. So in which direction you applied load, so this cross section, right? 5 into 100, right? So you need to be cautious with that while calculating, right? So this is how we are checking the result. So now, so we can check with see in this PPT we so because of this param post we are getting .op2. Did we get op2 or not? Right? So we got op2. So now we can change this. Okay, so now we can change the deck. Instead of -1, we can go ahead, we can change in Hypermesh also, or in we can change in IFI deck also. You can enter 0 here. Now I'll export the same thing, right? So now you can see So parampos 0 is there. Then run the same file, you will get xdb abort. So now you got xdb file, right? So now you can do the post processing using this also. Right? So you can see the animation too. Right? So you can see the stress, whatever the result you want, you can get it using those things. Stress, movement, right? This is the stress value what we are getting. So another thing I just want to discuss. So what is that? So we requested in load step, we requested sort 1, right? Sort 1. So what does it mean? So what you need to do, you can check with this static, open this file, edit with notepad. So this, whatever the file you are seeing, this F06 file is there, no? So this file, so which will help to check the fatal, whether fatal is there or what in the model, means error are there or not. So another thing is, so which will write, means it will print the results. So you can see displacement vector, see what are the, so they are in the form of column format, right? See, this is the format. So now I'll change this. So you can delete this. Then close. Now I can change sort 1 to sort 2, right? So where exactly we are doing? We are doing at load step, right? See, this is the load step where exactly we edited. So we entered sort 2. So then what you need to do, you need to run once again. So now you can see, open with Notepad++. So now you can see the displacement or stress vector, how they printed. This is the displacement vector, right? Stress vector. So this is how we are checking. So in sort 1 we are getting in grid format, so means vertical column. This is horizontal format, what you will get it, right? So you can change, only you can see those things which will represent in your F6 file, right? So another thing what you need to check is, so whatever the result we are getting, so after analyzing, so we are this is a simple plate, right? So whatever the value, simple formula you are using, and whatever the stress and displacement you are getting, you need to check with that. We can cross verify what are the result you are getting. Generally what happens, as number of elements increases, stress will show higher stress, as it is a so simple model, right? So for this what you need to do is, so you can keep two numbers, so you will get whatever the hand calculation you did, the same result you will get. So if you are keeping only two element or a one element, so because it is a regular cross section, right? So regular cross section, if it is a complex feature is there at that time, so it it have a effect. So that's why wherever complex features are there, you need to do fine meshing, and remaining area you need to do coarse meshing. This is what so specifically if you want to carry out a structural means stress based analysis, at that time you need to think that whenever you are going to decide element size, so which plays very important role. If it is a planar area, so what you need to do, simple random mesh, coarse mesh you need to do, and you can get a whatever the right result, you will get it. If it is a complex feature, at that time what you need to do, you need to do wherever complex feature is there you need to do fine mesh and remaining area coarse. So which will yield means which will give approximate good results. Thank you. Have a wonderful class. So I hope you guys enjoyed the presentation. So I am requesting you all guys, you can subscribe and share with your friends. Thank you and all.